In this video, we're going to look at graphing functions of the form y is equal to a to the x, where a is a positive constant. These are exponential functions and they're often used to model growth or decay. So we can see now that the variable is the power. This is just a constant, so we might have y is equal to 2 to the x, 4 to the x, 1/2 to the x. We can see now a is greater than 0 as these now are not defined for negative values, and also we say a is not going to be equal to 1. If we have 1 to the x, we end up with a straight line. What we're going to do is consider two different scenarios. We'll consider when a is going to be greater than 1 and then when a is going to be between 0 and 1. So let's now look at a greater than 1. So an example might be 2 to the x, 3 to the x, 5 to the x. We might even have e to the x, which is the exponential function. We study e to the x later on. So let's just draw a quick sketch, and what we've got now is our coordinate axis. All of these will have a similar shape, so we'll have them looking something like so. So we will get very steep, very big, very quickly. Unless we transform the curve in any way, we will have the point now 0, 1. That is where the curve will pass the y-axis. So if we consider now 2 to the power 0 is 1, 3 to the power 0 is 1, they will all go through the same point unless transformed. We also have the x-axis as an asymptote. We know that y is equal to a to the x can never be 0, 2 to the x can never be 0, 3 to the x can't. So we have this asymptote. As our value of x gets large, so we can say as x tends to positive infinity, y also gets very large, and y tends to positive infinity. So let's say we've got y is equal to 3 to the power of x. This is a positive constant and it's greater than 1. If we think 3 to the power of 0 is going to give us 1, 3 to the power of 1 is going to give us 3, 3 to the power of 2 is going to give us 9, 3 to the power of 3, 27, then we're going to get 81, 243, and then we're going to keep going up 729, and it's going to get very steep very quickly. We can say as x tends to negative infinity, which is going to be going in this direction, y is going to tend to 0. It will never be 0, and that's why we have the asymptote. So, unless these graphs are transformed, y is equal to a to the x, where a is greater than 1, will look something like so. It will pass through the point 0, 1, and we will have now the x-axis as an asymptote. Let's now consider when a is going to be between 0 and 1, and these, of course, are not included. We're going to now have a scenario where we're modelling decay. So if we look at this now, we'll go the other way. So what we've got then is the scenario now where we have, and we'll do an example of this. This time we will come through, and now the curve will come down, and the x-axis will still be an asymptote. This point will still be 0, 1. So let's say we've got y is equal to 1/2 to the power of x. So our value of a is a positive constant, and now we're between 0 and 1. Again, we have this x-axis as the asymptote, so we can go ahead and put that on. If we consider now what happens as x gets very large, we can say as x tends to positive infinity, y will tend to 0. We can say as x tends to negative infinity, y will tend to positive infinity. So y is going to get very large. Now, if we look at this here, y is equal to 1/2 to the x. I could actually write this now as y is equal to 2 to the power of -1 raised to the power of x. Using the rules of indices, a to the power of m raised to the power of n is a to the power of m multiplied by n. So we could actually write this now as y is equal to 2 to the power of -x. Now if we consider writing it like this, what we have is a reflection in the y-axis. This is of the form now, if we go back to our graph transformations, f of -x. So we can see the relationship between now y is equal to 1/2 to the x and y is equal to 2 to the x. So we have now a reflection in the y-axis. So for example, now if I drew y is equal to 1/3 of the x, then what we'd have just here now is the mirror image, and it would be reflected, and that would model now decay. And if you think about it quite clearly, as a value of x gets very large, negative, this is going to end up getting very big. So if we think about it now, let's say we had 1/2 to the power of -3. We could write this now, turning the fraction upside down and making it positive. We could have 2 to the power 3, which is going to give us 8. So on this particular curve, let's go ahead and put this just here. Let's say we've got -3, 8, and we can see that this is going to get very big very quickly. Yet if I take this point right here now, when x is going to be equal to 2, if we consider now subbing that in, we're going to have 2, 1/4. So that we can see, as the value of x gets very big, this is going to tend to 0. It will never be 0, it will never be negative, it just tends now to 0. Let's look at graphing some of these now on a graphical calculator. So we have y is equal to a to the x plus b. So this b is just a constant. As we can see, if we have 1 to the power of x, it's a straight line. 1 to the power 1, 1 to the power 2, and so on and so forth. If I now increase the value of a to b 2, we can see that we start to form now this exponential curve. So it's going to get very big very quickly. On this particular graphing package, we don't have the asymptote shown, but we end up now seeing that that is the x-axis. If I make this 3 to the x, we're going to have a steeper curve, and that makes sense. 2 to the power of 1 is going to give us 2, 3 to the power of 1 is going to give us 3. So this is going to get steeper. So as I increase that value, we can see we're getting very, very steep, and that is going to start giving us very large values very quickly. So for example, now if we take this to 6, y is equal to 6 to the x, 6 to the power of 0 is 1, 6 to the power of 1 is 6, 6 squared is 36, 6 cubed is 216, and so on and so forth. So let's get back down now to y is equal to 2 to the x. So here is our exponential function. Our constant a is going to be 2. What I'm now going to do is add a constant. So if I add 1 to it now, what we're going to have is y is equal to 2 to the x plus 1. The asymptote, although not shown, has moved up from the x-axis to the line y is equal to 1. So this can never be 1 or less. If we just consider now, as small or as big negative as this value gets here, this will get very small, but it will never be 1 or less. And we can see moving this now will just increase the asymptote. So we've got now the asymptote here at y is equal to 3. We could go the other way. If I put this down to, let's say, -3, then we've got now the line y is equal to -3. So this now gives us a brief example or understanding of what's going on for values of a greater than 1. So if we go back, what we're now going to do is look at values of a that are going to be between 0 and 1. If I move this back now, we can see that I'm taking this down. So this is 3/4 to the x. So we can see again it goes through 0, 1, and we're going to get now very small as x gets very large. And as we now take this value back, we can see this is going to get steeper and steeper. So if we just put it there, that is now pretty much 1/3 to the x. So we can see now that this is going to be a reflection in the y-axis of 3 to the x, as that's 1/3, which is 3 to the -1. Again, we can move this up and down, and we will have a change in the asymptote. So that gives us a rough idea of what we've got. All of the graph transformations that you've met before can be applied to these curves. So what we're going to do is just work through some basic questions and look at